Hello, everyone, and welcome. Welcome to the APSC 132 final exam preparation session. I'm so happy that you are joining me here today for this lovely time. I want to give you a general breakdown of what we're going to be doing, how we're going to be spending our time over the next couple days. The major focus for the live sessions is going to be for the two new sections of the course, specifically kinetics and electrochemistry. So we will be really taking our time and going deep into those different sections. If you're feeling sketchy on some of the pre-midterm stuff, there are two possibilities to bring yourself up to snuff on that. Possibility number one is to check out the posted on-demand videos. So for these on-demand videos, I've broken them down into two different sections, a bunch of quizzes and lessons. And I encourage you to, if you're unsure of what you know, try the quizzes first, and then only study the stuff that you're shaky on. I'll also be highlighting at the end of tomorrow the different areas that I expect to be tested in the most detail. I'll be saying that as we go through today and tomorrow, but I will give a summary of what I really expect to be on the exam tomorrow. All right, so we have our lovely preface here. Most importantly, probably for us, are the two breaks. We're going to have a break at 6:15 and at 7:40. 6:15 and 7:40. Tomorrow, of course, they're going to be different because we have a different timeline, but they're going to be the same type of thing, an hour and 15 minutes in and 2 hours, 40 minutes in. I'm sure that many of you have been to these things before, but just in case, I'll let you know that we're going to be doing lots and lots of problems today and tomorrow. And I'm really going to be focusing on how to answer the problems you're likely to see on your exam. Well, of course, you will be getting some chemical and engineering understanding through today and tomorrow. The focus really is to excel on your exam. So where there are shortcuts available, we'll be taking them. Where there are mnemonics or mental tricks, we'll be using them. The goal is to get that high mark. We have an absolutely gigantic supplement. Frankly, I think I probably went a little overkill on this. So like in the midterm, I will be saying, here are the questions that if you can only do 10 questions, here are probably the most useful 10 questions. But just in case you are an absolute rock star, you already know pretty much everything and you just want to pound away at a bunch of questions, you got them. These questions are a mixture between the knowledge development questions, which I wasn't really impressed with the solutions for. They're called solutions, but really they're mostly answers. So I will be going through a bunch of those. Some of the multiple choice, but frankly, the multiple choice was not particularly useful for the midterm. And as a result, we are only going to be doing bits and pieces of the multiple choice. That's especially true for kinetics. Like if you completely ignored all of the multiple choice for kinetics, you'd be totally fine. I think the electrochemistry multiple choice are actually considerably better than the kinetics ones and more indicative of what you're going to see on the exam. But because the exam is long answer, we will be mostly doing long answer stuff. I've also, though, added a bunch of what I called custom problems. So sometimes I would look at the samples provided and I'd be like, they aren't covering everything in as much detail as I want, or maybe they're completely omitting a really obvious thing. So for example, I would say that the steady state approximation questions that you were given in the knowledge development questions, I think they're a little bit off the mark in what you're going to be tested on for your exam. So I've got some other versions, some other questions custom for this so that we can practice and fill in those gaps. Solutions to everything. How long did this wind up being? All 80 pages of the supplement will be posted. I'll be submitting them sometime on Saturday, right after the session, and it normally takes admin about a day to finish that up, so it'll be posted sometime on Sunday. So you got tons and tons of solutions. Oh my goodness, they're really quite something. This thing is under copyright. So frankly, if your friend needs like a page or two of it, by all means, send your friend a couple screenshots or whatever. But please don't post anything publicly, especially large portions. If you have questions, then please post them on the Facebook group. However, I also understand that Facebook is a little bit boomer-tastic, and not everybody loves Zucker. So as a result, I will also give you my email address. My email address is mikemchem@gmail.com. mikemchem@gmail.com. You can also, of course, ask questions anytime throughout today. And I've always got my Q&A open just to the side here. So I'll always have that, I'll always notice when you ask a question. Okay, my goodness, are we done the prelude? Oh, I guess I should introduce myself a little bit. But I imagine most people here know who I am. I did my undergrad in nanoscience, and then partway through picked up a minor in chemistry, and then decided to do my master's in chemical engineering, where we were purifying nickel from the stuff up in Sudbury. Because they had a problem where their yield for nickel purification, nickel oxide to pure nickel, was kind of sketch. So it ranged from like 90 to 95 to 96% yield. And when you're dealing with tons and tons of nickel, that kind of range is just not okay. So we help them brush up that yield a little bit. And then with my PhD, I took up chemistry education research, researching how people learn chemistry and how instructors like myself can teach it in a way that is less painful and more useful. Okay, this breakdown of marks is not particularly useful anymore, as I'm sure we all know. So we can just continue on here. We are starting out today with chemical kinetics. So I've got a lovely little review page. If you feel like you know everything about chemical kinetics, just give this page a read. And if everything makes total sense to you, then you're probably okay. We're starting out here with reaction rates. So these are going to be what I also call relative rates. The idea here is that we have some kind of reaction, and I think it's pretty obvious that these are not all going to change concentrations at the same rate. That idea of a change in concentration over time, that is what we call rate. And I think it's nice to write it as rate, because if you write it as like delta A over delta T, I don't know, it just kind of looks scarier. But if you write it as rate, to me, it's not too bad. So based on our stoichiometric coefficients, we can probably get some kind of intuitive understanding of how these things work. So for example, let's say that I had a rate of the overall reaction of, let's call this, I'll call it 2 moles molar per second. So the entire reaction is going at 2 molar per second. Let's imagine the coefficient on A, let's make it 3. How fast am I making A? Probably got it even before I finished writing this out. I'm going to be making A at 2 times 3. Because for every time the reaction goes, I'm using 3A. So this is going to be 6 molar per second. But there are a couple little, well, there's one little nuance here, and that is this change in concentration, is it going to be positive or negative? It's going to be negative, right? Because this is a reactant, So it's going to be used up. So the change in concentration is going to be lower because the concentration is going down. So we throw a little negative sign in front of there, and that's why both of our reactants have negative signs there. Okay, but then what does this big equation actually tell us then? This big equation actually tells us how to relate the reaction rate, which was 2 here, equal to the rate of A over delta T, delta A over delta T. So we'd have 1 over 3. That is the stoichiometric coefficient. And then times that delta A over delta T. And you see, if we isolate for delta A over delta T, then we get the exact same thing. We come out with -6 molar per second. So all of that is to say, you can use this equation if you want, but your intuition is probably good enough, at least for relatively straightforward questions like this. Sometimes you'll also see this written as nu. And that means the same type of thing. It means the stoichiometric coefficient, but the negative sign is contained within the nu here. So in this case, nu of A would be equal to what? Nu of A would be equal to -3. Negative because it's a reactant, and 3 because that's the stoichiometric coefficient. All right, lovely, lovely. With that in mind, please try these 3 questions. When you're done, please let me know in the polls. Ten seconds remaining. All right. Always good to see those answers or those results coming in near the end there. Thanks so much for sticking with it. It's always good to see. So if the aluminum solid is lost at this rate, how much are all these other things happening? So this reaction is a little bit more difficult. Our intuition is probably not quite as strong on it. So what I'm going to do is say, I'm going to do this last one first. What is the rate of the overall reaction? Well, if we're losing this at 20 millimoles per second, millimolar per second, and the change in aluminum is going 4 times faster than the change in the overall reaction. And all we need to do is divide that by 4. And as a result, this is going to be 5 millimolar per second. It's a little bit weird to talk about an overall reaction as having a concentration, but you can use it in order to find other stuff. So then how fast is oxygen consumed? Well, the oxygen concentration is going to be changing 3 times faster than the overall rate. So we're going to have 15 millimolar per second. And then for the aluminum oxide, we're going to be having times 2. We're going to be having 10 millimolar per second. All right, lovely, lovely. Let's see a similar type of question in our kinetic study problems. So please go to page 18 and do question 3. Good luck. "20 seconds remaining. Okay. Most impressive, my friends, seeing 82% of people selecting answer choice E, which is our correct answer. If you selected an answer really early, I'm going to encourage you to spend a little bit more time with these. Early on, there was almost an even mix between C, D, and E. I will be giving you sufficient time to do these things, so don't feel the need to lock in early. But if I do give you that 10-second warning, it's always good to put in your answer because number 1, it helps you commit under uncertainty, which is a useful skill. And number 2, it helps me to know which answer choices to spend the most time on. So if we picked D, then we were saying that there is a 1-to-1 ratio between our N2O5 and our oxygen. And that's not the case, because the only way that we could have the same rates would be if they have the same ratio. Not the case, so D is out. There is a 2-to-1 ratio, so we're either going to be multiplying by 1 or dividing, or multiplying by 2 or dividing by 2. And that represents choices C and E. So we can try to use some intuition here and say that the change in concentration of oxygen is going to be less, it's going to be slower than the change in concentration of N2O5, just because every time the reaction happens, you lose 2 N2O5s, you only gain 1 oxygen. And as a result, we can just say that that's going to be the same as dividing by 2 and making E our best answer. But I know that I have been kind of leaning on intuition a lot. So if you're like, Mike, I hate when you're doing that, I'm going to give you another way as well. And this other way is thinking about units. If we want the rate of O2, and we want to put that in terms of the rate of something else, in this case, the rate of N2O5, we can do this with a stoichiometric ratio. So I'm just going to say molar ratio here. And then I'll be more specific in this next step. So our rate of O2 is going to be equal to our rate of N2O5. And I'm going to be so specific here. 1.2 times 10 to the negative 4 moles of N2O5 per liter times second. And I'll show you why I'm being so specific here. Because if we want to cancel moles of N2O5, then we can do that by putting the stoichiometric ratio of N2O5 on the bottom. And if we want this to be in moles of oxygen, then we're going to need to put moles of oxygen on the top. We have its stoichiometric coefficient, which is 1, so we can show it if we want to, but no pressure. And that is the exact same math as what we just did. Either way, we come out with 6 times 10 to the negative 5 molar per second. All right. So lovely. I could see that being part of a long question. So definitely worth nailing down. Next, we have our differential rate laws. And these are the things that look something like this. They're based on the reactants. So unlike equilibrium constants, they do not include the products. Very importantly is that you do not know the exponents on these just based on the overall reaction. If we're talking mechanisms, if we're talking elementary steps, by all means, sure. But we'll get into that later. Unless otherwise specified, you must learn these exponents experimentally. These exponents are called the order. So they're called the order with respect to whatever they're on. So this would be y order with respect to A. If y were equal to 1, then this reaction would be called first order with respect to A. If this were 2, if Z were 2, what would that say? How would you read that? You'd read it as second order with respect to B. And then if you want the overall reaction order, all you do is you add the 2 up. So it would be 1 plus 2, and this reaction would be said to be third order overall. All right, so now let's try to get some intuition for what all that means. If we have this reaction, and we say that it's first order with respect to C3H8, that means the exponent on C3H8 in our rate law would be 1. If it's second order with respect to O2, then that would be a square there. And this would be third order overall. Lovely. Let's do a relatively nice warm-up question here. Please try on page 18, question 1. A is true and B is false. So please let me know what you pick in the polls. Good luck. 10 seconds remaining. Okay, very nice. Seeing 78% of people selecting false here. False is our correct answer. So if we increase the concentration of A in a chemical reaction and that has no increase in the rate, what does that mean? Well, let's think about this mathematically. We have rate equals K times A, maybe some other stuff, but we don't know, we don't care. If we change this concentration, then it should affect the rate, right? That would be true if this were 1 or 2 or 5 or 1,000 or whatever, but it would not be true if this were 0. If this were 0, then the concentration of A does not affect the rate. All right. So what that means is that, therefore, I mean, they say there's no increase in rate. So therefore, this reaction is 0th order with respect to the concentration of A. Therefore, it's not first order. So false is our best answer here. All right, so let's hop back and let's do our method of initial rates. This thing is like almost guaranteed to be on your exam. Almost guaranteed, like over 90% chance you're going to see a question just like this. So it's good to have this thing locked in. Here's the idea. We want to make some kind of rate law. Let's imagine that we're doing rapid review question 1 here, and I want to make a rate law. Let me make sure I'm not cut off here. No, I'm good. So my rate is going to be equal to K times the concentrations of my reactants. I'm going to write that out. And I'm going to call this M, and I'm going to call this N, just because I need something to call these things. And I need to find these values based on these experimental data. So I'm going to show you the diligent way, and then I'm going to show you the quick way, which is going to work for if things are relatively simple. The diligent way is to think about putting a rate law on top of another rate law. So I'm going to erase this in just a sec, so don't actually write it down. But what would happen if we did something like rate 1 over rate 2? The equilibrium constants would cancel. Actually, maybe I'm not going to erase this. I am going to keep this up here because I think it's useful. This would be the concentration of 1 over the concentration of 2. This would be the concentration of 1 over the concentration of 2. And you can imagine this as all being in a big old bracket like so. Now, what's amazing about this is that the S2O8 2-, those concentrations are the same. So that allows us to completely ignore that part of everything. So we're then just going to have rate 1 over rate 2 is equal to the concentration of I minus for trial 1 over the concentration of I minus for trial 2, and that is to the power of M. We might as well finish this one up. So let's sub in some numbers and solve for M. See what you can do. You've got 60 seconds. Good luck. All right, let's go through it. So rate 1 over rate 2, we have 1.25 times 10 to the negative 5. We could put in units here, but they're just going to cancel in a sec anyway, so I'm not going to care too much. Over 6.25 times 10 to the negative 6. That's going to be equal to our concentration of I minus for number 1, 0.080 over 0.040. That was our concentration for trial 2. This is all to the m. Now, 90% of the time, 80% of the time, you are not going to have to do anything fancy here. This comes out to 2 equals 2 to the m. And as a result, we find that m is equal to 1. Now, there was a question in the Q&A, which was, why was S2O8 omitted? It was omitted because those concentrations are the same between both trials. And what that means is we're going to get 1 to the n. In fact, we can do this if we want to. But I will erase this in a sec. Times 1 to the n. And 1 to the power of anything is still just going to be 1. So as a result, it just doesn't affect anything. So, it sure was a lucky thing that I just happened to pick these 2 trials, so something canceled. But okay, you and I both know that's not luck. I've prepared for the class, blah, blah, blah. Here is what you want to be doing. If you want to find the exponent on m, you want to find the exponent on the concentration of I minus, you want the concentration of I minus to be constant. Said completely the wrong thing there, sorry. You want the concentration of I minus to change, because that's what's going to allow you to get this ratio. And you want the concentration of the other thing, S2O8 2-, to be constant. And again, that's for solving for m here. So what do you think I would write if I wanted to solve for n? What do I want to change? And what do I want to remain constant? Well, for n, I want the concentration of S2O8 2- to change. And I want the concentration of all the other stuff, in this case, there's only one other stuff, to be constant. Which trials do you see that happening in? Well, let's find where this remains constant. It only remains constant in 2 positions. Trial 1 and trial 3. So we cross our fingers, we hope that S2O8 2- remains constant there. It does, fantastic. So now we can set up our entire ratio and solve for n. I'd like you to please do that. Good luck, solve for n. Let me know when you're done. 10 seconds remaining. Okay. So I'm going to show this really diligently, and then I'm going to start showing you the shortcut. Because I did see 3 people get their answers in as done and confident within the first like 20 seconds. So I'm guessing those people already know the shortcut, and I want to share that info with you. So we're going to be using rate 1 and 3. Does it matter which one I put on top? It doesn't. I'm normally going to put the bigger one on top just to avoid fractions, but it's just making the math easy. You'll get the right answer either way. So we're doing 1 over 3. And those comes out to be probably giving you a feeling of deja vu here. We get 2 equals 2 to the n, and therefore n is equal to 1. So that is a fair bit of writing. And sometimes these questions use pretty friendly numbers like we're seeing here. At least the concentrations here are friendly. The rates are a little less friendly. That's fine. So given this, how can we do this super fast? Well, if we know we're using trials 1 and 3, and we've talked about how to pick that, I go like this, and I say this is times 2. I go like this, I punch it into my calculator and see that it's times 2. So then I wrote 2 to the n equals 2. And therefore n is equal to 1. If that didn't make any sense to you, that's totally fine. You can use the longer method. But if you were like, okay, great, now I can do these in 20 seconds, then that's great. Okay, so now let's do the last part, because we are not actually done. They also ask us to find the rate constant. Well, now we know the rate law. We know our exponents are m is 1 and n is also 1, so nice and simple that time. So all we need to do is pick any of these trials and sub in numbers. So what I'd like you to do here is please, I'm going to recommend trial 1, but you do you here. Sub in any of these numbers and find the rate law. Good luck. Okay, let's do it. So I'm subbing in my rate for trial 1, 1.25 times 10 to the negative 5. And that's going to be k times 0.08 times 0.04. And I come out with a k value of about 3.91 times 10 to the negative 1. 10 to the negative 3. But I have very conspicuously left units off of this. I left units off of this stuff because it was all going to ratio out, but I can't be leaving units off of my k. And in fact, sometimes they're going to ask, there's always like a mark for the units of k. So let's just make sure we know how to get them. Our rate was in molar per second. We don't know what k is. And these concentrations, well, they are concentrations, so they're going to be molar and molar. So my k then is going to be molar over second, molar, molar. And that's going to simplify to 1 over second molar. So my units on k then are 1 over second molar, and life's good. Now note that the units of k are actually going to change depending on the overall order. I'm imagining that you're probably pretty comfortable with unit canceling, but if you are not, here are the common ones that you're going to see. And if you want to just memorize an equation for all of them, that is there too. All right. We're going to do some practice problems, but please let me know how you're feeling about this so I know how hardcore to make the first couple problems. Okay, cool. So seeing a fair bit of confidence, then we are going to skip a couple of the easy ones. Let's start out with something medium difficulty. We're on page 18. Please try Q5. Good luck. Ten seconds remaining. Okay, let's take a look. Seeing an almost mixture between B through E, so we're going to do this in a fair bit of detail then. Which was the following statements about this, which is first order with respect to A, and first order overall is true. So how would we write that out? We would say rate is equal to K times the concentration of A, and we know that that is first order. Now, where do B or C come into these things? They don't. They don't need to. Because it's first order overall, which means if we add up all the exponents, we need to get 1. We already have 1, so there's going to be no other exponents here. So now let's read through our answer choices. B, the rate of reaction will decrease at higher concentrations of B and C. Concentrations of B and C are not going to affect anything. They do not appear in our rate law, so B is out. C, the time required for 1/2 of A to react is directly proportional to the quantity of A. So maybe, but this at least is a maybe so far. We haven't seen that idea. We will soon. So we'd put a little question mark there using good test writing skills. D, the rate of formation of C is twice the rate of reaction of A. So that's saying we are forming C twice as fast as using A. And this is incorrect. In order to make that happen, it would have to be A plus B, or A goes to B plus 2C. So in order for C to be changing twice as fast, it would have to have a stoichiometric coefficient of 2. So D is out. E, the initial rate doubles with a doubling of initial concentration of A. Yeah. If we double this concentration, what's going to happen to the rate? It's going to also double. So E is definitely true and therefore our best answer. We'll see C in probably, I don't know, 15 minutes or so, but we'll find out that that is incorrect. All right, let's do some really good knowledge development questions. So page 1, question 2. Good luck. I've put a hint up there. You have a minute and a half remaining. All right, let's talk through it. Seeing a little over 2/3 done, but nobody really feeling confident. So let's make sure we can knock these down. We know the rate law. This is based on interpreting this sentence. It's a 3 seconds, 1.5 order with A and 0th order with respect to everything else. So we just don't include anything else. What's going to happen if we double the concentration of A while holding B and C constant? Well, B and C still don't matter, so whatever. But if we're going to multiply this whole thing by 2, well, we're no longer just multiplying by 2, we're multiplying by 2 to the 3 halves. So, as a result, our new rate will be 2 to the 3 halves, or 2.83 times faster. If you wanted to, you could also think of it as like rate 2 over rate 1 is equal to concentration of A of 2 over concentration of A of 1 to the 3 halves. Same idea, just different way of writing it out. So use whichever method appeals to you more. Then what's the effect of doubling B? Nothing. No effect of doubling the concentration of B, at least assuming that you're not like changing the volume and therefore changing other concentrations, but it says we're holding the other ones constant, so changing the concentration of B is not going to affect anything. All right, let's do the next one, page 2, question 3. This is the absolute classic. This is the type of question that I am anticipating you seeing on your exam. Give it a go. I'm going to put a few hints up as stuff proceeds. Good luck. All right, your hints are up there for the first round. I will also say for this one, note that these are experimental data, and as a result, they are unlikely to be perfect. So I'm going to encourage you to round m to the nearest integer. It's going to be close to something. All right, keep fighting. You've got a couple minutes left. All right, let's wrap this one up. Seeing a fair bit of confidence here, looking strong, y'all. Our rate of 5 was 1.5 times 10 to the negative 3. Rate of 4 was 5.9 times 10 to the negative 5. And that's going to be equal to 1 over 0.2 rather, over 1. Nope, let's get that right. 1 over 0.2, sorry about that. And we come out with, I get about 22 equals 5m. So this is a little sketch, but like what could m possibly be here? If it's 1, then this should be a 1. If it's 2, then this should be a 25. That's pretty close. So I'm going to say that m is probably 2. Now, how would we do this if it were like really complicated? If it were really complicated, then what I'd do is I would take the ln of both sides. So I'd say ln of 22 equals ln of 5. And the nice thing about taking logs or lns, you can use either one, is that the exponent just comes out there. And we can solve for m as ln of 22 over ln of 5. And when we do that, we come out with 1.92, which is pretty darn good. It's pretty darn close to 2. This is a bit of a flex. I would be a little bit surprised if they asked you to do this, but maybe like 20-30% chance, so still worth knowing. There's a question in the Q&A, which was, why did we choose the 4th and 5th reactions for A? So for A, we're going to pick something when the concentration of B is consistent. And that way we can completely disregard B. That only happens in one of these situations, happens between experiments 4 and 5, so that's why I chose those. Now, if you wanted to, and in fact, I actually, when I was doing this question, I was like, you know, I'm not quite convinced, so I actually did check another experiment. So if you need to, you could go like, okay, we know when B doubles, we should expect this to double. So we should expect it to be 3.8 times 10 to the negative 3. But it's bigger than that. So this would be due to the change in the concentration of B. And then we could say, aha, but then this doubled, and we should expect that to be to the 2. That's what we're checking, right? So then we could further multiply by 2 to the 2, and we would get something very close to 1.5. When we did that, so we'd find that, yes, 2 makes sense, like the exponent on 2 makes sense. Now this kind of rationale, I think there's like a 5% chance or so that you're going to see that. So if that mostly didn't make a lot of sense, I wouldn't worry about that too much. But I did include that in my solutions, so you can always check those out if you are curious. I'll label this due to concentration of A. Okay, the last step was finding K. So to do that, I'm going to use trial 1. Because again, I am nice and uncreative. We're going to have rate equals K times, and we just sub in what we know. We know that M is equal to 2 and N is equal to 1. Fantastic. Plug in numbers here. I guess I'll isolate for K first. But this part is generally pretty uninspiring, not too exciting. There's not a lot that can really happen in this step. 1.5 times 10 to the negative 2. And I'll actually put units on this because they're going to matter. For our concentration of A, nice easy 1 molar squared. And for B, 2 molar. And we'd come out with 0.0075, 1 over molar squared seconds. So that is our final answer for this differential rate law. And again, this is the type of thing that I'm expecting to see. All right, let's pop on over. And we're going to briefly look at instantaneous versus average rate. Whenever you hear instantaneous rate, I want you to think about tangent lines or derivatives. So if they ask you like the instantaneous rate of the disappearance of A at 5 seconds, find 5 seconds, boom, and then we draw a line. Now you can draw a line like this if you want, but I like to draw my lines all the way through the axes because that way I don't have to think too hard when I'm doing my rise over run. I'm going to try to draw a relatively straight line here. It's not terrible. We want it to be straight at that point. Needs to turn a little bit there. Yeah, okay, we're going to go with that. That's not bad. Maybe a little more turny. Something like that. And if you do have to do these, they will give you a fair bit of leeway here. So how do we find the rate at time 5? We use rise over run. So how far did this rise? I'd say this rose, we'll call that 0.97. And minus, well, I'm going to go all the way down to 0.2. Be careful, they did not start this at 0. Over the run, which was, I'm going to call that 22 seconds. And this one, they did start at 0, so it's -0. And then, lovely, we can crunch that out. When we do, we get our rate equals 0.035. And what are the units on that? Units on rate are molar per second. So that is our final answer. What I'd like you to do is please now try 20 seconds and this average rate. Good luck. All right, let's talk them through. So at 20 seconds, I'm going to call that something like this. And that's going to be, I'm going to call that 0.73 minus 0.2 over, call that 29 seconds. And that comes out to be 0.0183 molar per second. And this gives me a qualitatively interesting thing. What is happening to my rate over time? Is my rate over time changing? Is it getting faster, slower? My rate over time is decreasing. And this is often going to be the case. Not always, but often, and we'll get into the details in the next section. The last one, if they're looking for the average rate of disappearance between 5 and 50, we just connect the dots. So 5 is here, 15 is here. Now we could just do that. But again, I just like to extend things all the way down and all the way up. Going to come out to be about the same there. Sure. So at 5 to 15, our rate is going to call that 0.93 minus 0.2 over. I'm going to call that, I drew it a little bit funny, but I'm going to call it 24 seconds. And as a result, I come out with 0.0304 molar per second. There we go, make that line up. There's a question, could you re-explain the blue writing? Yes. So what's happening to the rate? Early on, it was 0.035. Later on, it was 0.018. The rate has decreased. The rate is decreasing. It's going down over time. Why is it doing that? Well, because we started with a lot of our reactant, and now we just have less of our reactant to react, so it's not going to react as fast. All right, let's take some time. Let's shake it off. We're going to take our 10-minute break. During this break, I want you to please move around a bit to focus in your peripheral vision. These are the two things that will allow your brain to recover a lot faster. I'm telling you this because I used to take breaks completely wrong. I used to take breaks continuing to sit in my seat and to scroll Instagram, and that is narrowing my visual field and not moving. That's not what you want. That's not what you want to cause your brain to get back in the game. Come back in 10, and I'll talk to you then. All right, friends, we are back. When we last left our heroes, they had learned about instantaneous versus average rate, they had conquered relative rates, and they had rocked our integrated or our differential rate laws. Getting ahead of myself, because now we're going to page 9 and looking at these integrated rate laws. Now, I'll admit, I was a little bit surprised when I was looking at your equation sheet, because your equation sheet just doesn't have these on them. And if you have any insider information, by all means, please throw that in the Q&A. But yeah, I was just kind of surprised to not see any of it there. So I'm guessing they're expecting you to memorize it. But so that's how I'm going to teach it. But hopefully you'll be okay. Because integrated rate laws historically have been a fairly big focus. So they are definitely worth knowing. They look like these. And because they're not on your equation sheet, I'm going to try to teach you how to think about them in order to be able to remember them. So first, I want you to think about them as y equals mx plus b, so our linear lines. For a 0th order integrated rate law, the amount of reactant that you have is going to be equal to what you started with and then what you've used. So of course, the little knot there means what you've started with, your initial amount or initial concentration. And you might be looking at this, but like, what do you mean we're adding what we used? Well, remember that this little nu here for a reactant is going to be negative. So it's going to be what you started with minus what you've used. How do you know how much you've used? It's going to be kT, your rate constant, which is essentially like the velocity of your rate times t. So this is actually really, really similar to something like your position is equal to your initial position plus your speed, or I'll say your velocity. Yeah, I'll say your velocity times time. It's the exact same type of idea here. This is for a 0th order rate law. And what that means is that the speed of the rate does not depend on any concentrations. And we see that based off of our differential rate law, right? Because a to the 0 is just 1. Anything to the power of 0 is just 1. So we're going to have rate equals k, and therefore there is no dependence on concentration. I'm going to be really specific here, actually. The rate has no dependence on concentration. And you'll see why I'm being really, really precise with this in a second. Okay, so let's look at what this graph looks like. For a 0th order rate law, the rate does not depend on the concentration. So it's going down at a consistent rate, and it just keeps doing that until you're all out, and then flatlines. Flatlines. Then, what does a 1st order one look like? Well, we saw before our big punchline from our instantaneous versus average rate. The big punchline from that was that your rate slows down. And in fact, the data that we saw in the graph above, I modeled that as a 1st order rate. And we see the same type of thing. The slopes of these are different. The slopes are eventually becoming completely flat, but it's kind of this asymptotic-ish approach. Now, in order to remember this, we need to remember that first order involves lns. Other than that, it looks the exact same as what we saw before. So we have, instead of A, we have ln of A. Instead of A naught, we have ln of A naught. And this other part just stays exactly the same. And it's going to stay exactly the same through this whole thing, so life's pretty good. But then what happens if you look at a second order rate, or second order concentration versus time? It looks really similar to the first order, doesn't it? Like, they're not actually the same, but it looks really similar. So if that's the case, they're not going to bother to like give you these graphs, or if they do, they're going to give you a different graph that is more useful. And that is what's known as a linearized version. So for the linearized version, we're changing the y-axis. For the 0th order, it's concentration because it was already linear at the beginning. For first order, we now have ln, and hopefully that makes sense because our y equals mx plus b is in ln form. For our y-axis over here, we have 1 over concentration. For this one, this is the only one that's going to be upward sloping, and that's just because as 1 over concentration goes up, how does it do that? It's because the actual concentration goes down. You can remember that if you want, but I'm just going to encourage you to think qualitatively. You're going to lose your reactants. You're going to gain your products. So when you get to a final answer, just always make sure that this is true, and you'll be good. That will take into account, that will fix any of your pluses and minuses here. Now, if I were to guess, because they're not giving you these equations, I would guess that they are going to give you a graph and have you try to take the equation from the graph. That's my best guess. I'm not 100% sure on that, but I think that would be a way that would make sense for them to test you on this. So that's going to tell you that 0th order is just A, first order has the ln, and second order has the 1 over. If your brain is like coming out your ears right now, I will tell you that first order is the one that is tested by far the most. Probably 60% of the questions are first order. So that's nice, I guess. It means that that you can focus on that one. Second order is, I think, second most important. So we'll shrink that star a little bit. 0th order very rarely comes up in any kind of meaningful way. The last thing that I want to emphasize is the half-life equations. We can have half-life equations, and they are not too bad. What do they, how do we get them? Well, we take the ratio of A over A naught. And a half-life means that you have half of your stuff left. So what does that make that ratio? If you have half of your stuff left, what's that ratio? If you have half your stuff left, it's going to be 0.5. Okay. The last thing on this page is the little bit of trivia that's often tested, and that's looking at your K for your first order half-life. The important thing here is that your half-life does not depend on any concentrations. So that's really similar to what I said over here on our 0th order, but here it's the rate that has no dependence on concentration. Here it is on the right, so the 1st order, it is the half-life that does not depend on any concentration. Now, while we are still getting used to this, when we're doing our practice questions, I don't mind if you use this as your equation sheet, but you do want to treat this as a crutch. What do you do what do you use a crutch for? You use a crutch for when you're getting better, but you're not quite there yet. And then once you get better, what do you do with the crutch? You get rid of it. So this is a temporary help. Let's do some practice problems. Let's do 2018, question 14. This is an absolute classic style of question. Even though it's multiple choice, it's in the big multiple choice, so this could totally be part of a long answer question. Good luck. I'll give you some hints in a moment. Hints are up there. I've given you the equation that's going to be useful for you. See if you can follow these 2 steps. You're going to have to use this equation twice. Let me know what you pick when you're done. Good luck. Your last hints are up there. You have 1.5 minutes remaining. All right, looking good. Seeing 71% of people getting the right answer here. Nicely, nicely done. And about half of people finishing within that time, which is not bad at all. So first, I'm going to talk through what I did to get up to this point. First, we need to recognize that this is a first order reaction. And as a result, our equation that's going to be useful for us is this one. Now, previously, I had this VKT plus VKT. Because they specified that A was a reactant and it has a stoichiometric coefficient of 1 in front of it, I know my V, or my nu rather, is -1. Okay, so my equation turns into this, and first I'm going to try to find my K value. So I sub in the numbers that I have with the information that I have, and I find my K. Now I have a fully actualized equation. I am ready to rock with this thing because I know our K value. I can find a concentration at any time now. So that's what I'm going to do. My ln A, let's see, I want to find A. So I'm going to isolate for that. E to the, and this is a little bit silly, but the algebra is nice and simple if we write it that way. And we're going to come out with, oh, actually, I'll sub in my numbers. E to the ln of our A naught is still that 0.400. They mean molar there. There's a little typo. Minus our K, which we just found, 0.0313 times our 175. Just make sure that these units match. Always check these units. Sometimes they're going to try to throw you off. So we found this in minutes. We want to be working with minutes. This time it's great, but other times they have mucked around with that. And as a result, we come out with 1.67 times 10 to the -3 molar. And usually I'd talk through like how you could eliminate things a little bit faster, but frankly, we can't use elimination for this exam, so I'm not going to. All right, fantastic. Let's do, actually, let me first ask you, how are you feeling about this kind of thing now? Deciding whether to do 2 more questions or just 1? Okay, most people are like doing okay. So we're going to do just 1 more, but then I'll give you the question reference. So if you want to do more, you know what to do. So we're going to be doing this one here. Give it a look, give it a go. Good luck. Your hint is up there. You've got 60 seconds remaining. Okay, let's talk through it. So this question is a little bit strange in the sense that they're just asking you to find K. They tell us that the half-life is this. So let's isolate for K. That's 1, 2 over 5, 5, 7, 0. And we come out with 1.24 times 10 to the negative 4. And they ask us specifically for those units. Gave it away. They're asking us specifically for those units. Those are years. So the units on our final answer are years to the negative 1, or 1 over years. So this is our final answer here. Okay, based on how we're doing, I actually do want to do one more here. So please join me on 2017, getting our Wayback Machine. And please try question 71. Like usual, I will put up the equation that's useful. Just like last time, single reactant means our nu is negative 1, and that is very, very typical. I'll also write this other one. All right. Good luck. A few hints up there. Use them if you need them. Let me know when you're done and keep fighting the good fight. Good luck. All right, let's take a look at this first part. So we want to use the half-life equation to find K. We can do that by taking our T1/2 equals ln 2 over K. There have been a couple questions about this equation versus the equation that we saw previously, where the difference is we have this nu A and this negative. So because we keep dealing with things that are reactants, the nu is going to have a negative sign out front. And because the stoichiometric coefficients are usually 1, this just turns into -1, and these two things cancel. So that's why you keep seeing me writing this out as K equals ln 2 over T1/2, because frankly, this is kind of the more common version, and I'd be pretty surprised to see them mix in some stoich on the exam. So if you have to memorize things, I think this is the one that you're going to want to memorize. All right, so we solve for K, just like we did in the knowledge development question. Our T1/2, they tell us, is 180. So our K turns out to be 3.85 times 10 to the negative 3 seconds to the -1. So now what we want to do is we want to use this to find the ratio of how much we have over how much we started with. And this is kind of non-trivial in this case, so I'm impressed to see so many people finishing this, because it does require you to know a ln rule. So let's take our lns to the same side here. And the ln rule that we have to know is that when you are subtracting stuff like this, you can put them in the same ln. So now what we're going to do is we're going to take the ln to the other side. And like we've seen before, the opposite of a ln is an e. E to the negative kt, we just found our k to be this. And our t is 900. Again, make sure the units match. They do, so life's good. And as a result, our ratio here is covered by the Q&A. There we go. Our ratio here is 0.0313. Let's make sure that we've actually answered the question as requested. What percent of the sample remains unreacted at this much? So this is the fraction that remains unreacted. We better turn it into a percent. You just move the decimal place over 2 positions. 3.13%. Now, something that you can watch out for, and more often is useful as a check rather than actually getting the right answer, is sometimes they'll tell you the t1/2, and then the time will be an integer multiple of the t1/2. So if you start with 100%, how much do you have after 1 half-life? You have 50%. You just divided by 2. How much do you have after 2 half-lives? You have 25%. I'm also going to say 1 half-life is 180 seconds. 2 half-lives is 360 seconds. You can maybe see where I'm going with this. Oops, let's take that stroke with it. There we go. Three half-lives. Now going to be 540 seconds. Four half-lives, 720. And now we're down to 6.75. And 5 half-lives, would you look at that, is 900 seconds. So what are we going to have at 900 seconds? Did I just mess that up? I did just mess that up. We're going to have 3.125%. Look at that. It matches. So I think people were actually a little bit lucky there, and I'm guessing that very few people use that method, but it is totally valid. So you can use that as a way of checking an answer, or if you get lucky, you can find the answer explicitly using that method. All right, I think that is enough of integrated rate laws and half-lives. We're going to proceed right on. There is another kind of blah, blah, blah about rates of radioactive decay. This is just a rearranged version of our lovely first order half-life equation. So there's nothing new here. This is just a different version of our half-life equation, so nothing new there. We're going to proceed into transition state theory. Transition state theory is another real important part of your exam. Guaranteed you're going to see some kind of reaction progression diagram on your exam. With transition state theory, the idea here is that we're going to start at some energy. And sometimes they'll be vague and they'll just call it energy. Sometimes they'll be more specific and they'll call it Gibbs free energy or Gibbs energy. Any of those things all mean the same thing to us. We start at our reactants. And then we have to overcome some kind of activation barrier. This activation barrier is sometimes called your activation energy. You will also see it called your delta G double dagger. Now, these are not technically identical things, but they are practically the same thing for our purposes. The point is, it's the difference between our reactant and our peak. At the very top of this peak, you have what's known as the transition state. And that is the time when you have the very highest energy. So what happens here is the reactants are working and working and working and working, and they're putting in all this effort, and then, finally they can reap the benefits of all their work. They can retire. And in this case, the change in energy, or if we're calling this G, we can call this the change of Gibbs free energy, is negative. And in that case, this would be called exergonic. Oftentimes, we're going to use that interchangeably with exothermic. And that means that the products, are they going to be more stable or less stable than the reactants? Our products are going to be more stable than the reactants because they're lower energy, and low energy is more stable. I think I said this at the midterm, but I'm going to say it again because I love talking about it. In order to really internalize that low energy is more stable, I want you to think of a cat. If your cat is low energy, if your cat is basking in a sunbeam, then it is low energy and your entire house is stable. However, if your cat is full of energy, if it's doing its traditional 2 a.m. zoomies, then your cat is high energy and your entire house is unstable. So the high energy state here is the unstable position. We even see that in our activated complex. Our activated complex is the molecule or molecules at that highest energy. And like, look at this garbage bonding that's happening here. Like the carbon is kind of bonded to a triple bond. What? What kind of bonding is that? Kind of garbage bonding. And as a result, this is going to be really high energy. Nailing down some low-ish priority vocab here. Our delta H double dagger is the energy required to specifically distort the bonds. So like make them a little bit longer or twist them around a little bit in order to do the reaction. It's like your activation energy, but just like a subsection of it. And your delta S double dagger is the difference in entropy between the reactants and that transition state. So if they gave it to you like this, actually it would probably be more like this in this case, your delta S double dagger would be that. And just to complete the set, this would look something like this probably. What would your delta H double dagger be here? Your delta H double dagger would be that. Okay. So we can also have this for a multi-step reaction. And I want to try to give you some intuition for like how the molecules are suffering here. Let's imagine that this is me. I am benzene apparently. And you know, I am on my computer. And it's late at night. I sleep like an old person, so I like to go to bed at like ideally 10, but it doesn't happen very often. So I'm going to say this is me on my computer at 11 p.m. and I should not be on my computer at 11 p.m. I need to go to bed. And bed is way down here. Based on the relative energies between being on my computer and me being in bed, which of those do you think is more stable? going to be being in bed. But I think we've all experienced this, like we are watching YouTube or scrolling Twitter or scrolling TikTok on our phone or whatever. It takes some energy to like get up and actually do stuff. So even if at the end of the day, it's going to be lower energy and more stable to be in bed, it still takes some energy to get there. So I'm going to have to do two things. I'm going to have to shower because I shower in the evening. And the very transition state here would of course be getting out of the shower. It's the worst. It's so cold. It's high energy, and it is unstable. Then I've dried off, but I'm just kind of like standing around in the washroom at this point, and that is not particularly stable. It's better than like being wet in the washroom, but it is it's not as good as being in bed. But I've got to do one other thing first. I've got to brush my teeth. I've got to floss and all that. So this is all my like dental hygiene stuff. It takes another activation energy. We'd call this delta G double dagger of step 2. This would be delta G double dagger of step 1, if we're calling this G. All right, so now that I've flossed and made my dentist proud, I can finally get into bed. Get into bed. And maybe there would be like one more little peek as I get into cold covers and I have to like warm them up a little bit. But we'll just assume that that is a pretty seamless process. I totally missed a like thread joke there. Seamless process, whatever. So hopefully that gives you some intuition for like what all of these kinds of ups and downs really mean here. Let's now, actually, I want to do one more thing. What would be delta G double dagger of the reverse reaction? And specifically, I want delta G double dagger overall. So not of a particular step, but I want it overall. Well, it's going to be this. Because I'm starting over here, I'm starting on what used to be my products. And in order to eventually get to my reactants, what used to be my reactants, I now have to climb that huge activation barrier. So this would be delta G double dagger of the overall reverse reaction. And while we're at it, why don't we also label delta G, just delta G of the reverse reaction? All right. So our delta G of the forward reaction is going to be this. And I'm in fact going to even put a little arrow down there. And the delta G of the reverse is going to be the opposite of that. So it's going to be going up. To really drill this home, I'm going to tell you that the delta G of the reverse reaction is positive, and it's making this reaction less stable. All right, let's now do KKD question 4, part 2. So we're on page 3. Question 4, part 2. Good luck. Your hints are up there. You have 60 seconds remaining. All right, let's talk this through. We want to sketch this diagram for a thermodynamically reversible reaction with slow kinetic rates. So thermodynamically reversible means that the reactants and products are roughly the same energy. That means they're going to look something like this. If you have like one a little bit higher, a little bit lower, that's totally fine, but they've got to be really close. Then, if there is a slow kinetic rate, that means it's difficult to do. If it's difficult to do, that means that there is a very high activation barrier. So I'm going to draw this in one step. It's going to be a really big activation barrier. And that gets me my marks. I love questions like this because if you know how to do them, they take you 30 seconds, which, so much better than having to like follow negatives through calculations and all that stuff. Ugh. All right, let's pop back now. And let's look at the lovely Arrhenius equation. Now, the Arrhenius equation is a little bit weird because they give it to you in a not particularly useful form. So they give it to you like this. Let's take a look at our equation sheet. Just make sure I'm not talking spit. Yep, we see it in the top right there. And you're almost never going to use it in this way. You might use it qualitatively. You might say that as the activation energy goes up, this is negative, so this entire thing is going to go down, and therefore the rate constant will go down. That would be one way of doing it. I'll do another example. As the temperature goes up, this entire term is also going to go up. Let's break that down, actually. This part is going to go down because the temperature is in the denominator. But because this thing has a negative in front of it, if the absolute value goes down and it's negative, then the actual value is going up. And if the actual value is going up, then our rate constant is going up. If you want a TLDR of this, if your activation energy goes up, your rate constant goes down. If your temperature goes up, then your rate constant goes up. And especially that second one, well, okay, I'd say both of these should feel about right. Like if your EA, if your delta G double dagger is big, if it's hard to get over the activation barrier, then the reaction is going to be slow and the rate constant is going to be low. But if our temperature is high, that means the particles have lots and lots of energy and are able to overcome that activation barrier. So again, this might be used qualitatively. We can rearrange it in terms of our lawns, but even then, it's not particularly useful. What is useful is if you use this equation twice. And you can either do that like really, really diligently with lots of math, or you can do it like I'm going to show you here. You have ln 1, or a K1 and K2 at two different temperatures. And if you think about dividing these, actually better yet, let's subtract them. Yeah, let's subtract them. So we're going to have ln. It's going to give me an upside down version of what I want. So I'm going to switch these. There we go. So if we subtract these, what do we get? Ln K2 minus ln K1 equals ln A minus ln A. The A is a constant. It's called an Arrhenius constant or a pre-exponential factor. But the point is, it's always going to be the same. So they're just going to cancel out. And you're going to be left with negative EA over RT2 minus negative EA over RT1. We can rearrange that like we saw before. If you subtract the stuff in lns, then you get this lovely fraction instead. Positive one goes on top, the negative one goes on the bottom. We can factor some stuff out here. We can say negative EA over R, 1 over T2 minus 1 over T1. And this is by far the much more useful version of the Arrhenius equation. One other thing here. Oh, and of course you can also just like straight up choose to memorize that equation. That's fine too. If you do, I remember this as the EAR equation. EA over R, the EAR equation. All right, so one other thing here. It's possible you'll see an Arrhenius plot. I'd be a little bit surprised at maybe like 20–30% chance you're going to see an Arrhenius plot. It's going to be ln of k, so ln of this. And we're going to have an x-axis of 1 over k, so 1 over our temperature. And this slope is going to be this term here. And again, if you are not particularly happy with math, then you can just straight up memorize that, and that'll be just fine. Let's do a few examples here. Oh, and actually, one more thing. And that is, when we're talking the Arrhenius equation, when we're talking about these k's, these are what I call simple k's. So more on this later, but this is not like k observed. You know how sometimes when we deal with mechanisms, we get like this rate constant vomit. We've got some like equilibrium constants in there, and it's like k2 times k1, and then k negative 1 and all that kind of stuff. If you've got something really funky like that, then the Arrhenius equation might not work. It'll like kind of work, but it won't be perfect. And they might ask you some kind of conceptual question about that. All right, let's do KKD. Page 3, question 3. Good luck. I've put a hint up there. Even if this looks super annoying, I am going to highly encourage you to do this at least a couple times until you start getting right answers here. I will tell you that it is very easy to mess this up on your calculator. People do it all the time. It's me. I am people. I've messed up this so many times in my first few years of classes. Keep fighting with it. Get an answer. Show me when you're done. Good luck. All right, let's wrap this one up. We've got this. We need to make sure that we are consistent with which one is K1 and which one is K2. If you want, you can also say like K at, let's see, what's K2 here? K at 675 and K at 298. You can write whatever you want for your subscripts there. I find that that really helps some people. But we want to isolate for EA. Okay, so we're going to have negative R and ln of all this stuff. And all over, and here's where this can get like really nasty with your calculator. All right, we can sub in values here. So we're going to have negative 8.314 joules per mole Kelvin times ln of second one on the top, 45 over 33. Just make sure they have the same units because we want those to cancel. That's good. Big brackets, 1 over T2, 675, minus 1 over T1, 298. And when we crunch that all out, we get 1376 joules per mole. You should always have a positive activation energy. If you don't, you probably dropped this negative. I say that because I've dropped that negative before and it's no fun. So again, as usual, think qualitatively first. Please let me know how you're feeling with that kind of thing. Okay. Okay, seeing mostly pretty strong here. So then I am going to just give you a couple question references. So if you want more, you can do the 2018 exam question 23, and 2019 exam, part C, question 6. So this is a tough multiple choice question, and this is a long answer question. Feel free to tune your experience to what you need. And now, my friends, we are getting into reaction mechanisms. These can be pretty gnarly at times, but you will definitely be seeing these, so they are definitely worth knowing. Actually, I'm going to keep this star for when we actually see the type of thing we're going to see. Because, I mean, you know mechanisms is going to be on it in general, but I want to tell you exactly what's going to be on it. So first, what is a mechanism? It's a series of elementary steps. It's a series of reactions that show every single step. It's not skipping anything. These elementary steps are just those single steps. They don't skip anything. The overall reaction is going to be the sum of all of the elementary steps. So you add all the steps together, you get the overall reaction. This is just like Hess's law. And then an intermediate is going to be formed in one step and consumed in a later step. When we're figuring out a mechanism, it obviously has to be consistent with experiments. I think that's pretty obvious, but I say that because a lot of times they'll ask you like, which of the following rate laws is consistent, or which of the following mechanisms is consistent with this rate law? So you can come up with a rate law based off of the mechanism and then compare it with the given rate law. And when we add up all those individual steps, the overall reaction based on the mechanism has to be the same as the actual overall reaction. Let's nail down some easy vocab. We can have uni, bi, or ter molecular reactions. Unimolecular reactions, well, just the first part in general, means what you're starting with. So a unimolecular reaction, uni meaning one, like a unicycle, starts with 1. Bimolecular reactions, bi meaning 2, like bisexual, starts with 2 things. And termolecular, I don't know if we actually use ter in any kind of normal daily life, but at least it starts with T, which starts with 3. So you're going to start with 3 things. Now, unimolecular reactions, easy peasy, lemon squeezy. You only need one thing and it breaks apart, so you're not exactly demanding a lot out of your mechanism here. So unimolecular reactions, great. With bimolecular reactions, these are a little bit trickier. They're a little bit trickier because you need 2 things to happen at once. You need these 2 things to combine. But also, I mean, did you see how I did that with my hands? Like, they need to not only combine, but they need to combine in the proper orientation. Because when 2 things are coming together, they can't just adapt to different orientations very easily. Molecules are not that fast. There's only one thing in the world that is that fast, that can adapt orientations that quickly, and that is, of course, Snoop Dogg. Only Snoop Dogg can adjust his orientation from a fist bump to a handshake in real time. No molecules can compete. No other people can compete. Smooth Dogg is super, of course. Snoop Dogg is super smooth. So bimolecular is like harder, but still not that bad. I mean, you can do a handshake, like not with too much difficulty. But with a termolecular reaction, this is straight up tough. because not only do you, it would be like trying to get three people to handshake at once, except they're all just like moving around randomly because that's what molecules do. So that's not going to happen very often. You might get asked a qualitative question about that. There was one in the knowledge development questions being like, why are termoleculars so slow or so rare? Because they're hard. You need three things to happen all at once, and it's just unlikely. All right. When we're talking about mechanisms, we are going to really care quite a lot about what we call the slow step. Now I'm going to zoom in on just me here. The slow step is going to be similar to if two people are walking together. Let's say you and a friend are walking together. You are the gloved hand. So I got a glove over here. And your friend is this bare hand. So if you're walking together, let's say that you are 6 foot tall and your friend is 5'3". And you could walk faster, right? You could just like speed away from them. But that wouldn't make you a very good friend, right? So instead, you are going to match their pace. One sec. Oh, goodness me. Okay, you are going to match their pace. So you are going to be walking at the same speed as them. Which one of them is rate determining? Your friend is rate determining in this example. Your friend is literally the slow stepper. So your friend is the slow step. If we're talking about rates of reaction, the only thing we care about, the only step we care about is the slow step. So that is always where we are going to start. And for mechanisms, not for anything else, but just for mechanisms, we can write the rate law based off of the reaction. Which reaction? Not the overall reaction. The slow step. So we can write it based off of that, NO2 and NO2 again. And not only that, but the exponents actually come from the stoichiometric coefficients. Now then, you do have to make sure that this does not have any intermediates in it. Remember that intermediates are formed and then consumed. But do you see any intermediates based on this mechanism? See if you can find one or two or just one. One thing is formed and then consumed, so that is an intermediate. Now that is nowhere in our rate law, so life is good. We can just put our feet up because, probably write it more reasonably, we now have our rate law. One other thing, they're specifically telling us that this is K1, so we shouldn't be vague. We should call it K1. All right, so that's a nice first easy example. As you know, these can get pretty funky. Let's take a little break first. Let's shake out our brains. Please come back in 10, and I'll talk to you then. All right, friends, we are back. We are back and looking at some hardcore mechanisms in a second. First, I just want to make sure that we have the easy stuff locked down. So please try rapid review question 2. Good luck. All right, this one is a little tricky, so I'm going to drop in and give a hint. Initially, we would be using our slope step. We'd say rate equals K2, they specify K2, times NO and O. However, we have an intermediate. We are not allowed to have intermediates in our overall rate law. So we're going to use what's known as the rapid equilibrium assumption. There are two main assumptions we need to know for this course: steady state assumption and rapid equilibrium assumption. Here they tell us that the first step is a rapid equilibrium. They show us the equilibrium arrows, and we have K1 and K negative 1. K1 means the forward reaction of the equilibrium. K negative 1 means the reverse reaction of the equilibrium. So we need to use that equilibrium in order to get rid of this O. What just happened? There we go. So we need to pull out our equilibrium knowledge from way back when and say that our equilibrium is going to be K1 over K negative 1. It's the rate constant of the forward reaction over the rate constant of the reverse reaction. And that is going to be what? Going to be product over reactants. Hopefully it rings some bells. And we're talking about this middle reaction, so make sure you're using that middle reaction here. Lovely. Okay, so I don't see any big K's in my answer choices, so I'm going to get rid of that. Now what I need to do is isolate for O and then sub in. You've got a couple minutes left. See what you can do. Good luck. All right, let's talk this through. We want to isolate for oxygen. Okay, so we're going to have O equals K1 over K negative 1, O3 over O2. And then we're going to sub it into that above equation. So I'm going to cheat a little bit and just take this whole thing and sub it right in there. You can, of course, skip to that second step. That's what I would recommend here. And where does that leave us? Well, we have K2 on the numerator, so that eliminates B. We have, let's see, we don't have any atomic oxygen anymore because we got rid of that, so that's good. And then we do have something on the denominator. We have O2 on the denominator, so D is out. We can make sure that A matches. It does. So A is our best answer here. All right. Now, there's one other thing that I want to mention here, and that's very often they're going to roll all of the K's all up into one. So that's going to look like rate equals K, and then it'll say like experimental or observed or something like that. And that's just fine too. So sometimes they'll do that, sometimes they won't, just something to be ready for. And this is an example of what I was describing as a complex K. It's got a bunch of K's in it, so the Arrhenius equation is not going to work perfectly. Let's see an example of this. Let's go to question 9 here. We're on page 8, question 9. This one really is the toughest type of version that you can possibly see. Give this a go. Good luck. Your first awfully sad hint is up there. Let me know when you're done. Good luck. Your second of 3 hints are up there. You've got a few minutes left. All right, going to talk a little bit more. We've used the equilibrium expressions to find these big, ugly equations. Now we're going to sub those into our initial rate law. So my rate law starts out as this. And then for CLO, well, I'm going to write it out from the beginning here. Rate equals K3. And then NOCL, so we have this whole shebang. And CLO, so we have this whole shebang. And where does that leave us? Well, let's see if anything cancels. The ClO2s cancel. The N2Os cancel. So we have rate constants for days. But these actually are not going to matter because at the end of the day, we're just going to say K experimental anyway. And then what are we left with here? NO2Cl squared and NO2 on the bottom there. All right. How do we use that information to answer this question? You've got a minute or so. Is there any way to make this work? Good luck. All right. It is underwhelming, I'm afraid, but we can't make this work. The only way that this could work would be if the concentration of NO2 were equal to the concentration of NO2Cl. And it just doesn't make any sense. Like, if we tried to use K, the second equilibrium constant here, and we tried to relate those two concentrations, we just see that like they're going to be related by a bunch of different factors. This is probably even overkill just to say that this and this are not the same. So unfortunately, this is not consistent with the experimental rate law. Don't you hate it when they bluff you like that? That's such a dissatisfying finish to a question. That gets a big sad face. But we will get some cooler endings here when we look at our steady state approximation. So we're on page 17 now. I love the steady state approximation because once you know how to do it, it's super mechanical. You get a bajillion marks for it because you got to show tons and tons of work, and it's just a dream. And also, you're practically guaranteed to see it. So when are we going to use a steady state approximation? In theory, under these two circumstances, but realistically, when told to. They will practically always tell you explicitly to use the steady state approximation. That's how it's been in all of our practice questions. I think they even said that explicitly in one of the classes. So like, they're going to tell you to. The idea here is that you have two steps, both alike in dignity. And these two steps look something like this. You start out with some kind of equilibrium that's making a reactive intermediate. And this reactive intermediate then reacts and forms C in this case. But what are we going to do with this thing? Because like, what if this is not fast? What if we can't use the rapid equilibrium approximation? So then we've got to get a little bit more involved. But the idea here is that this is going to be making R. This is going to be removing R. And one of two things could happen. Either eventually these two rates are going to be equal, and you're going to be making R and you're going to be using R. There's always going to be a constant amount of R left. One might say R has a steady state. The other possibility is you're making R faster than you're using R. But what would happen if that were the case? What would happen if you're making lots and lots of R? If you make so much of it, eventually this reaction is going to start going backwards, and you're actually going to fall into the first case. So under either of these conditions, the assumption that you have a constant amount of your equilibrium, of your intermediate, is going to be a very good assumption. So what does that mean? If we have a constant concentration of R, that means that the rate of production of R and the rate of loss of R, the rate of consumption of R, are going to be equal. So these two are equal to each other, and therefore when you add them up, they get you 0. So conceptually, that is nice and straightforward-ish, at least. And then expressing it mathematically, again, it just takes a bunch of lines of math, so we're going to get a bunch of marks for it. I'm even going to just keep this, put it over here so we don't forget what this looks like. So if we're saying that the rate of production of R and the rate of consumption of R are the same, but opposite, like they're going to be the same but equal, then we can just write out all of the different ways that we can form or use up R. Let's look at the equilibrium first. So the forward direction is producing R, right? The forward direction is producing R, great. The backwards reaction is using up R. Produce, consume. What's this last one doing? Consuming or producing? It is consuming. And now here's the magic, and here is where you're going to get all the marks. All you need to do is say that the rate of producing is equal to the rate of consuming. So what is the rate of producing R here? This is just what we've been doing with all of our mechanism stuff. We would say the rate is equal to K1 times A, concentration, times B concentration. Okay. So that's the rate of producing. What about consuming? Write that out. I'll give you a hint. They're going to be two. You're going to have to add them up. Okay. So we're going to have K -1 concentration of R plus K2 also concentration of R, because again, we're just taking the reactants. So then we apply our steady state approximation. We say those two things are going to be equal to each other. And this is dead easy. We literally just say this is equal to this. Amazing. Okay, so that's great, but like, why does that matter? How is this useful to us? I'm just going to keep that around for us. So now we can do the same type of thing as we did before. We're going to start with the later step in this case. Doesn't have to be the slow step. Watch out, there's a little spacing error there. So if we don't know anything about the rates of these, we just start with the last step and we write it like that. But obviously we have a problem. This is in terms of an intermediate. So what do we need to do? What do you think we're going to do with this lovely thing? Like before, we're going to isolate for the thing we want to get rid of. And then we're going to sub that in to the initial rate law. So take a sec, try to work that out. Good luck. Okay. So we're going to isolate for R. I'm going to show this really explicitly. We're going to factor this thing. So K -1 plus K2. And we're going to take that whole thing to the other side. And that is all equal to the concentration of R. Lovely, lovely. We're then going to sub in. the initial rate law. That was rate is equal to K2 R. So what's that's going to become? Going to become this gigantic thing. And that, is it in terms of any of our intermediates? No, it's perfect. It's great. We're done. And as you can imagine, we just got like 5 or 10 or whatever marks. Tons and tons of marks. Love it. There were a lot of steps there, so let's summarize. 1, we're going to write our initial rate law. And this is going to be based on the last step. Two, write rates for all ways to consume and produce your intermediate. Three, isolate for the intermediate. And then we sub in we sub that into 1. All right. Now, I'm just going to tell you straight up here that the next 2 parts are just not particularly important. So we're going to breeze through this, and then we're going to look at the final boss of kinetics. We can have a flooding or isolation method. If you have a huge amount of something, then that amount practically doesn't change. And instead of writing this out as Ka and B, you can just write this out. Oh, there should be a K there. You can just write this out as some other K and B if we have tons and tons of A, because if we have tons and tons of A, it's not changing. Like this amount of change is like so small. It's like, I don't know, what is that? 5%, under 5%? Whereas this amount of change is like 100%. And in that case, again, we just ignore this little difference. Okay. And we have Michaelis-Menten kinetics. I was even surprised to see this mentioned at all, because this is like more biochemy type stuff. So the idea here, the only thing that I could see them maybe saying is like something qualitative about when you would use it. It's when you have a fast first step and a slow second step. And it's usually, again, some kind of enzyme. I'm not going to talk about it very much. Instead, we are now going to go to an absolute banger of a question. Summarizes practically everything in kinetics. And that is the stuff on page 14 and 15. Okay, got to zoom way out because we need to be able to see everything here. Once again, we're on page 14. Give this a read. Don't get intimidated by all of the stuff that's all over the page. Like it's there. If you want to, just call them like A, B, C, D, whatever. Good luck. Your hint is up there. See if you can wrap up part A. Please let me know how you're doing. All right, I put the rate laws based on each of these mechanisms up there. See if you can use that information to answer part A. You have 1 minute remaining. All right. So what's the difference between these two mechanisms? Well, first of all, how did we come up with these rate laws? I named this big scary thing A because we're close. We're on like first name basis. So if the first step is rate determining in both reactions, what that means is that you just have to look at the first step. You cross your fingers and hope there are no intermediates in there, and there are no intermediates on the reactant side of the first step. I mean, there literally can't be, because intermediates have to be formed first. So if it's a reactant in your very first step, it hasn't been formed. So that's great. That tells us that mechanism 1 says that the rate depends on just the concentration of this big sucker. Whereas mechanism 2 says that the rate determines on both of these. So how are we going to experimentally determine which one is correct? You run 2 trials with different concentrations of our Nouch. And then see if it affects rate. If you get different rates, which one is correct? If you get different rates, then Mechanism 2 is correct. Okay, now please try part B. Let me know when you're done. Good luck. Okay. So what is going to give us a linear graph? Mechanism 1 is first order. So if we're plotting some concentration against time, do you remember which one first order is? Is it just concentration? It's not going to be ln concentration. So ln concentration is our answer here. Okay. Now let's move on to the next page. And again, this continues our final boss here. They've been nice and labeled these for you, so you don't need to try to write big things, just A, B+, and C. Please try part A. You have just 60 seconds for that. Let me know when you're done. Good luck. Okay, let's go through it. What's the overall net reaction? Well, we have A going to B, and then we're using up B. So B is an intermediate. As a result, it's just straight up A going to C. Lovely, lovely. Oh, there's a little cyanide in there. Never good when you miss cyanide. So we have A plus cyanide going to C. And there's a little bit of bromide over there too. So it's going to look like so. Now at the end, you should always make sure that your charges are going to balance. We see that our charges balance, so life's good. We can have some confidence that we're going to be having the correct answer here. All right. Now they ask us in a few different steps to use our steady state approximation. So please start out with B. If you get bored, you can go over to C. Good luck. All right, I'm going to put some hints up here. We want to make our steady state approximation because we want to get rid of B. So what is going to consume B? B is only going to be consumed by this. Oh no, it's going to be consumed by two things. It's going to be consumed by the reverse of that first equilibrium. So K -1 times concentration of B plus and concentration of Br minus. And it is also going to be consumed by the second reaction, B plus and Cn minus. Okay, lovely, lovely. How is it going to be produced? See if you can wrap that up and then wrap up the rest of B. Good luck. All right, so to produce this thing, we're going to be using the forward direction of this equilibrium. So we're going to have K of 1 times A. Is there anything else reacting there? Nope, nothing else reacting, so that's a nice easy one. Because we're using the steady state approximation, these two things are going to be equal. So we're just going to say this big ol' thing is equal to this tiny little thing. We want to isolate for B plus. So we're going to do that. And when we do so, we come out with, I'm going to lose my color coding here. We come out with K1A divided by a huge thing. Our K -1 concentration of Br minus plus K2 concentration of cyanide. All right, so we've derived an expression for the concentration of B plus in terms of everything else. And now finally, we need to sum this all in. So please take a minute and a half to do that. Good luck. All right. So we're subbing 4 into 1. We're subbing this thing into the initial rate. So our initial rate would be, oops, I circled the wrong thing there. Our initial rate, second step. That would be rate equals K2 times the concentration of B plus times the concentration of cyanide. And we've just gone to all of that trouble to get rid of B plus, so let's get rid of it. Take this whole thing. And remember to include your cyanide at the end. And I know when copying and pasting, I always have to give a little extra time. So please do let me know if I ever move on too quickly. I'm happy to always flip back, or after class, happy to go back and check anything. All right, amazing. So this is something we will absolutely need to have locked down for our exam. Tons and tons of marks. They're easy marks once you know them. It's not like some things where you can make a lot of careless mistakes. These ones, for whatever reason, tend to work out okay. All right, so we are going to just crack open a little bit of electrochemistry. We're on page 35 here. Electrochemistry is going to have what are known as redox reactions. Redox is a mix of reduction and oxidation. Oxidation is when something loses electrons, and reduction is when it gains electrons. And there are lots of ways you can remember this. Like some people like to remember oil rig. Oxidation is loss. Reduction is gain. But another way of thinking about this, and I think my personal favorite way of thinking about this, is in terms of oxidation states. Oxidation is when you increase an oxidation state. Reduction is when you reduce or decrease an oxidation state. Now, sometimes they're going to be a little bit tricky on you, and they'll talk about oxidizing agents or reducing agents. So think about, like, what does a cleaning agent do? It doesn't clean itself, it cleans something else. So an oxidizing agent is going to oxidize something else. And where this can get a little bit confusing is that an oxidizing agent, in oxidizing something else, itself becomes reduced. Similarly, a reducing agent is going to become oxidized. All right, so we've got an example here. The oxidation number on zinc goes from 0 to 2 plus. Is this oxidation or is this reduction? Well, did the oxidation number go up? Did. So this is oxidation. We could alternatively go from +1 down to 0. That number is decreasing, and as a result, that is reduction. And now we get to a very scary looking page. But I'm going to tell you that this entire thing can be summarized in 2.5 rules. I put the 2 rules at the top there. I'll give you the half in a sec. Rule number 1. The sum of all oxidation numbers for all the atoms in a molecule is going to add up to the overall charge. Let's look at some trivial examples and then ones that are a little bit more exciting. So for N2, you have 2 nitrogens and they're the same nitrogen, right? We passed APSC 131, so we know N2 is going to look like that. And put in lone pairs if we really want to flex. But The point is, you have two of the same thing, and it's got to add up to 0. Oh, this is not the most complex math we've done all day. We have 2x equals 0, x is equal to 0. No need to think about like imaginary numbers or anything like that. It's chemistry, the math is normally not that bad. So if you just have the same stuff adding up to 0, it's always just all going to be 0. What if you have something that needs to add up to -1? Well, it's got to be -1. What if you have something that needs to add up to -2? It's going to be -2. But what happens if we don't have all of the same thing? What happens if we have some mixture like HCl? Well, now we don't quite know. HCl needs to have oxidation states that add up to its overall charge, which is 0. But this could be 0 and 0, could be -1, +1, could be +1, -1. We don't know. We need to move on to the next rule. Next rule says that elements want their columns charge. Let me show you what I mean by that. When we go to our lovely periodic table, and I'm going to rotate this so you don't have to be like an owl. So what do I mean by they want their charge? I want you to think about how many columns they are away from the noble gases. So fluorine, what does it need to do to become like a noble gas? It needs to move one column over to the right. And from an electron point of view, what does that represent? It represents fluorine getting an extra electron. So this would be -1. Fluorine likes to be -1. And the exact same argument applies for everything in that column. So chlorine likes to be -1, bromine likes to be -1. You get the idea. With one column more to the left, same argument applies, but now it's got to hop over 2 columns, meaning oxygen likes to be -2, sulfur likes to be -2, probably getting the idea, nitrogen likes to be -3. But what happens when we get to carbon, silicon, etc.? They can actually go in either direction. So I can go 1, 2, 3, 4, gain 4 electrons to become -4. Or it can go 1, 2, 3, 4. Lose 4 electrons to become +4. And once we get to boron, we get the entire switch. Because now boron prefers to go 1, 2, 3. Beryllium likes to be +2, hydrogen and its entire column like to be +1. Okay. So now we have actually nailed like most of these rules. We've done that one. We've done that one. We've done these ones. But there's one exception that I want to deal with here. And that exception is what happens if the atoms don't all get what they want. So first, let's imagine like H2O. What does hydrogen want here? Hydrogen wants +1, and there are 2 of them totaling +2. What does oxygen want? Oxygen wants -2. There's only one of it, totaling -2. And when we add these up, we get the overall charge, which is 0. Amazing! But that was a case where everything got what it wanted. What would happen if we had the nastier molecule, oxygen dichloride? So in that case, oxygen wants -2, chlorine wants -1, so that's -2 and -2 total, and it's adding up to -4? That's not okay. So one of these is going to have to lose electrons. Which one do you think is going to lose electrons? Or put differently, which one of these is going to pull electrons harder? It's going to be the oxygen, because the oxygen has that greater electronegativity. We learned about our Frenkel elements last semester. And what that means is the oxygen is going to pull those electrons away from the chlorine. The chlorine is going to lose the electrons. Lo and behold, we've managed to satisfy our first rule. Amazing. So with those 2.5 rules, we have summarized this entire page. Life is great. What I'd like you to do now is please assign the oxidation numbers on, actually, I'm going to help you with the first one. Tin chloride. We know what chlorine wants. Chlorine wants -1, but tin is like way over here. If you get too deep in the periodic table, like these things just go wild. They can do whatever they want, or they just get kind of pushed around by anything, I mean. So chlorine is going to be -1 each, totaling -2. And that means tin must be, we're using deductive reasoning here, tin must be +2, because these things need to add up to 0 for the overall charge. Please find the oxidation states on each atom for tin chlorine on the right, tin 4 chloride. Good luck. All right. So for chlorine, wants to be -1. That's going to total -4. Tin gets pushed around. What must it be in order for this to add up to the charge of 0? Got to be +4. Woo. All right, friends, we are going to call it there. I hope that you've had a super useful session. I imagine some brains are like oozing out your ears. If you have any questions, please throw them in the Q&A. I'm turning it over now to the Q&A. And if you're not sticking around for the Q&A, that is totally fine. I hope you have an exceptional rest of your night, and I look forward to talking to you tomorrow morning. Yeah, you're welcome. Thanks for coming. All right, last call. If you're in the middle of typing something, please click submit so that I know I should continue waiting. Okay, looking like nothing there, so I'm going to call it here then. Hope you all had a lovely time, and I look forward to talking to you tomorrow. Take care.